to the cloud. Anyhow.
5 divides 100, you said?
Yeah, 5 divides 100. 5 times 20 is 100. See, but it's an English thing now, right? That's the way we say it in English. We say that 5 is a divisor of 100, or we say 5 divides 20. Why are you making that face? You don't say that before? And also, we have other synonyms. We might say 100 is, we could say 5 divides 20. 5 divides 100.
What do you mean 5 divides 20?
What is 5 times 4?
20.
Right, so that means that we're saying 5 is a divisor of 20, or it divides 20. Well, you don't have to like how that's how we say it. It's not whether you like it or not.
Say it 5 divides 20.
Yes.
I say what's the 20 divided by 5?
You could say it that way. That's 2 ways to say the same thing.
Yeah, I don't like that.
Anyhow, well, you don't have to like.
Last interruption.
Yes.
How was your daughter's virtual school?
It was good, actually. It went well. Yeah, she liked it. She likes being in school, though, better.
Did they just change that?
No, they just wanted to do it as a test run in case things go sour over the next few weeks or months. Who knows?
Her arm is okay.
She's fine. Yeah. That's the little one. She's a crazy. You don't have to worry about her. All right. So here we need to know some facts about these things. This turns out to be important. So suppose that A, B, and C are integers with A not being 0, because you can't divide by 0. This, by the way, this is an important theorem, so we might as well state it as such. And we're going to ask you to prove it, parts of it for homework. So there's 3 things that happen here. Number 1, if A divides B and A divides C, then A must divide their sum. So these are basic facts about numbers and dividing. If A divides B, then A divides BC. And then the last thing is if A divides B and B divides C, then A divides C. So it's useful, before we prove this, it's nice to just see explicit examples of this to illustrate what we're saying. So the first one, take, for example, 3 divides 21 and 3 divides 15. So 3 divides its sum, which is 21 plus 15, which is 36. Four divides 20. So 4 must divide 20 times k for any k that's an integer. So I'm using a different letter. Instead of C, I'm using K. And then lastly, let's look at the third one in action. Say 5 divides 15, and 15 divides, say, 60. So 5 divides 60. So what I'm doing is instead of writing this theorem out in general, well, I shouldn't say instead, I've written it out in general. But now I just gave you 3 examples that show them in action. Yes?
The second one, you said like 4 divides 20k for any k.
Yeah.
It can be anything. Not in
That's true, but that's correct. It doesn't have to be. Well, again, that's not necessarily true, because if it's not an integer, then there's nothing to say that 20 times k is an integer. So then dividing doesn't make sense. I mean, take Say k is 1.5.
Still it divides to 20.
What if k is 0.6?
Still it divides
Does it by our definition?
by 20, like 5. It's going to be 300 or something. Still, it just divides.
What if k is pi?
Still, pi, it's going to be 5 pi.
Right, but pi is not an integer.
But still it divides.
No, our definition of divide says that it has to be two integers. That's correct. So really, and I get what you're trying to say, and you're not completely wrong. But remember, we're dealing only here right now with integers. So you can pretend that we don't even care about numbers like pi, or we don't care about numbers like
Complex numbers,
1/3.
it still divides.
Well, but our definition is divides means you have to have an integer. Divides means there has to be an integer. That's what it means. That's our definition of divides. Now, we're gonna also, we can divide, but look. So maybe this is a language thing. I know what you mean by divides, but the definition we have is that we say A divides B. We're not talking about the action of dividing one number into another. We're going to do that shortly, because we know when we take a number into another, we might have a remainder, correct? So that's a different thing than saying A divides B, or saying 4 divides 20. So when what we defined on Monday is the phrase A divides B. We didn't define division. Do you understand that? That's two different topics. I don't know if that's clear. And you got to make sure that you understand it. We're not defining division. We assume there's this operation, but we haven't defined it yet. Think about that. We haven't defined it. All right. So we're going to do that in a second, though. Here's another important theorem that we need to use. So if A divides B, again, A and B are integers. And so when we talk about dividing, it has to meet this definition that it's a multiple of two integers. So if A divides B and A divides C, then more is true. Then A divides MB plus NC for any integers, M and N. Okay, now let me reiterate what this means. When I write A divides B, that definition in context says that A and B are integers and A is non-zero. That is context. So now what we're going to do is we're going to technically, I guess you could think of what we're going to do now is we're going to define division. So how do we define it? How are we going to define this notion of division that you've been using since you were a child? What is the proper way of defining it? And so the way we do it is we call it the division algorithm. Which is funny because it's really not an algorithm. But that's what it's been called forever, so that's what we're going to call it. So here we go. Suppose A is any integer and D is a positive integer. then there exist unique integers Q and R. And here's the important fact. And by the way, you're choosing these letters so that you might remember some of these words. Yeah. Yeah. So why are we choosing D and Q and R? Well, you might remember words from your childhood like divisor, quotient, remainder. That's what you should be thinking about with these numbers.
So I learned English. I didn't know why I used D, Q, R.
Yeah.
Always meant like
Zero.
Where?
0 or D.
Yeah, that's 0. It has to be a positive number. That just means it's positive. Now look, this is not difficult. You've done this before. This is what this is saying is you can take any integer, divide it by any other integer, and you can always write it like this. Always. Right? So let's pick an integer. Let's look at some examples. So let's take, say, how about the number 37? 37 is equal to, for example, 5 times 7 plus 2, right? $63. One way to write 63 is 10 times 6 plus 3. Alternatively, how could you write this? Yeah, you might write, another way to think about this is you might say, for example, 37 over 5 is 7 plus 2/5, or 63 over 10 is 6 plus 3 over 10. So these are two ways to write the same thing. Do you understand that? Now, of course, what we're saying is this rational number doesn't necessarily have to be expressed that way. We can express it in terms of integers. So this is a nice way. We have two different ways to describe the same relationship. That's the point we're saying. So again, I remind you that that's why we're using Q here. We think of Q as the quotient, and then D is the divisor, and R is the remainder. So there's some notation that people like to use. So it's common to write the following. It's common to write Q, that's our quotient, and we write it as A, and then we say divisor, or D. And then we might also write R equals A, and then we put mod, M-O-D, D. Now again, so we're telling you this is a common notation. So it's common to write this when A equals, yeah, well, let's keep it, yeah, so let's keep it consistent, DQ plus R. So if we again use some old words, You know, we might say this is the divisor. You might say this is the quotient. And our old friend from elementary school, the remainder. So let's just knock out a quick example to illustrate this. So let's divide, say, 120 by, I don't know, how about 13? So if I do that, what is 120? Well, 120 would be equal to 13. How many times does 13 go into 120? Well, 13 would go into, if I multiply 13 by 10, I get 130, right? So it's going to be 9, right? So what's 13 times 9? 13, yeah, well, slow down. Why we got to go so fast? Where's the fire, right?
You will just, you know.
So 9 times 3 is 27, carry the 2.
13,
Yeah.
13 minus 13.
Oh, wait, okay, but you're going, yeah, but okay, good. You're actually, so you, does that mean you already know how to do GCDs now? Have you done that before? Huh? So I think that's what you're alluding to. We call that, do you know what that's called? Do you remember what it's called?
I don't
Well,
know what's called in English.
But that we'll be getting to that shortly as well. All right, anyhow, 13 times 9 is 117, so you can write this as plus 3. And so how would we write this? Well, we'd say, okay, Q, so we say 9 equals 120 divide, and then your D is 13, and then 3 is your remainder when 120 is divided by, excuse me, mod. Write mod now. It's just notation right now. We're going to define something similar in a second. This is notation. Yeah, yeah. It leads to something you use every day and you don't realize that it's math. How do you tell time? How many numbers do you use to tell time? Depends on where you live. In the United States, you basically use 12 numbers, 0 through 11, or 1, whatever. The rest of the world uses 24, right? What happens when it's, right now it's 11:37 a.m. What time will it be in 2 hours? Right, so when was the last time 11 plus 2 is equal to 1? You're going to find out. It's called modular arithmetic. You use it every day. Yeah, that's what we're getting to. Oy vey. So why is this notation useful? Basically, look here. So no, to get to your point, if you look at this up here, this R business, why is this useful? Because we're saying that what this mod means is what is the remainder when you take A and divide it by D? Turns out the remainder is a key. Remainder holds all this and very useful information about numbers. I mean, the best case scenario is that the remainder is 0. That means a number divides, well, in school you would say evenly in, right? Isn't that kind of what you'd say as kids? But so we'll sort of get to that and soon enough. But yeah, we're leading to something.
I remember when we were coding to find out the prime numbers, we were using this, you know, remind us, like, God. You know what I mean?
Uh-huh.
To find out, like, 1, 2, like we will just count down 1 to the half of the number, and we will find out that.
Well, yeah. Do you know why you only have to do the square root of half? Yeah.
If it doesn't divide, that's prime numbers.
That's correct. So that's right. That's called the sieve of Aristophanes, which is a way to list all the prime numbers. So, okay, so let me build on your point and also Mackenzie's. It turns out that when we want to learn things about numbers, one of the best ways to do that is to just look at the remainder when we divide one number into the other. It happens to be useful information. You know, just like when we study water, from one perspective, it's better to look at it as two things of hydrogen and one thing of oxygen, right? So what we're getting to is when we want to study numbers, why not we study their building blocks? And their building blocks, as some of you might already know, are the prime numbers. Those are the prime numbers. Any number that's an integer can be really its properties and how it plays with other integers depends really only on its prime factors. And we're going to find that that's very important. And so one of the ways you understand how to find prime factors and how to work with them is, and we're going to get to prime numbers in a second, is you have to understand this concept of remainders. And so what we do is we create what's called modular arithmetic. We want to create a very efficient way of doing math so that when we say we're going to tell time 2 hours from now, it's not 1340, it's 140. Does that make sense? And why would we do that? Well, let's think about it. If I add, think about how natural this is. Right now it's 1140. If I add 2 to that, think about how I'm adding it. Right now I'm adding, so I add 2 to that, it becomes 1340, but we don't use 13. So what's the remainder there? Okay, well, how many times?
1.
No, it's not 1.
2.
2, right? So it
Okay,
turns
what
out
are you
that,
talking
yeah.
about?
What do you mean, what am I talking about?
Wait, 11 plus 2 is 13.
You mean you're gonna just.
Okay, okay,
So you're gonna take
correct. Yes, okay, so that's how you get your number. So how do you know what it's going to be 2 hours from now?
You're gonna add 2 divided.
Right, but that's not how you want to do it efficiently. There's a better way. It comes down to the remainder.
Okay. So
What is the remainder when you divide 11? Okay, let me ask you this. What's the
Same thing,
Yeah.
same thing.
what's your question?
So if you were like, okay, so it's 11:40, we're gonna, in 2 hours, the time will be.
Yeah.
So because we use like the number up to the 12 system, the 12.
The only numbers we're using are 1 through 12, right?
12 goes to the 13 once, then there's a remainder 1, and then it's 140.
Okay, yeah, or you can think about it as how many times does 11 go into 12? Well, hang on. Well, look, I think I'm confusing you right now. Let's define something and then we'll look at the examples. So
what we're gonna do is going to, for example, 1140, right? We're gonna add 1 with 11, it's gonna be 12, and
Yeah.
we're gonna divide 12. The remainder is gonna be 0, and we're gonna add 2. Why? Because we're gonna
okay, so what we're going to write now is we're going to write something that's similar to this mod thing, but it's different. But it's related. So let's consider 2 integers, A and B. Now, what we'd like to know is what happens if we take a number and divide it into A minus B. Turns out this is useful. So if M is a positive, actually, I'm going to use N. I'm going to use N, not M, because there's too many M's floating around. That becomes confusing. So if N is a positive integer, we write A 3 bars B. This is going to scare the hell out of you. Mod N. If
this is bigger than.
if N divides A minus B. So what happens if this is true? We say A is congruent to B modulo That's all of us, we, the community of people who study this. Modulo N. So let's write this down. We got to do an example right away. So modulo, M-O-D-U-L-O. We just defined it. We just defined it for you. It's a new word.
Where's it defined?
Right here. We just said if this relationship holds, we define modulo N. That's what it means. So let's look at an example. Yeah, that's right. Take, for example, 10. 10 is congruent to 2 mod 4. Why? Well, since 4 divides 10 minus 2, which is 8.
You can domino numbers, I just wanted to find out what modulo means. Right now I have moduli.
Oh, that's moduli. That's fine. That's the plural of it.
Biggest question, how do you know this?
All right, let's look at another one. How about 27 is congruent to, say, 6 mod 7, since 7 is confusing. You're learning something new. It's not supposed to be easy. I mean, what is 10 minus 2? 8. Does 4 divide 8? Yes. So we're creating a new. We know that 4 divides 8, and we also know that 8 is the same as 10 minus 2. Because
how would you ask us a problem?
What do you mean?
On our homework, what would be would you give us something, or
I could say determine whether this is a congruence relationship or not. We'll get to that. You'll see. Yeah, of course you're confused. What is it with you guys wanting to understand things in 30 seconds? That's not how we learn anything. No, it's not. I mean, you have to understand that many things can't just be, they're not obvious, right? I'm just making this up right now. I'm telling you this is a true thing. Why do we write this? Why do we write this? Because this is a fact. Why do we write this? Because this is a fact.
Oh, so we're gonna write the first thing after you.
It depends. You can go one way or the other way. It depends on what we're doing. We might move left to right. We might move right to left.
So you could just prove it by doing that.
We're not proving anything. This is an example.
Not prove it.
Right. Well, this is the definition. This is new notation for an old fact. Do you understand that?
Yeah.
If we have a fact, we are saying this particular fact can be expressed in this new notation. It turns out, believe it or not, this notation has its uses. You just don't see it yet because you just learned it. Right now, it's hard for you to understand why this notation is useful. When I get that, you learned it 30 seconds ago. Learned of it 30 seconds. You didn't learn it. So you want a very simple question that I can ask you? Like here's a simple question I might ask a beginner. You might say, is say 17 congruent to 7 mod I don't know, say mod 8. Okay, well, for this to be true, you would need 8 to divide 17 minus 7, which is the same thing as 8 dividing 10. Does 8 divide 10? This ain't true. So the answer to your question is no. But to sort of run this example to the ground, what is a true relationship? However, since 5 divides 10, 17 is congruent to 7 mod 5. Now, how do we write that in this, the new notation? We would say 17 congruent 7 mod 5. I could also say to you, I could give you two integers, Mackenzie, and say, okay, when are for what modulo are they congruent to each other? And then you would have to think about it. Like, think about this, 17, 7. How many numbers can I divide into 10? Well, I can divide 1, right? That works. I can divide 2, 5, and 10. That's it. So there's only four moduli for 17 and 7.
There's an expression Q is equal M plus 1 times.
Yeah, there's all kinds of theorems that we can derive and deduce, yeah.
Wait, so how would that one work?
What do you mean?
But you would have 5 divide.
Okay, let's write it down. So we can also, you also have 17 congruent to 7 mod 1. 17 would be congruent to 7 mod 2. 17 congruent to 7 mod 5. And then 17 congruent to 7 mod 10. Those are the only ones that make any sense.
Yeah, but then you set it up like whatever the mod is.
Yeah, but
And then parentheses like 17 minus 7.
say that again.
You would set it up in the other way, like you have.
You mean write it in terms of divisibility? Well, right.
Like for mod 2, it'd be like 2 divides.
Yeah, right. So for example, this thing right here, if I think this is what you're saying, 2 divides 17 minus 7.
Yeah, like
right?
that's how you would.
1 divides 17 minus 7, right? 5 divides 17 minus 7. Of course, I know 17 minus 7 is 10, but I want you to see the pattern here. Does that make sense? Yeah. Yeah, it should be. Good thinking. Way to be observant. That's all right. There's no rush. I don't see a fire. That's the second time I used that. I love water. Here's a cool fact. And this is a theorem, so we're going to write it down. And again, look, this is, you ain't going to learn this in an hour. You're just not. You need to have experience with this over a period of time. Now, you're going to say, well, we don't have much time. Obviously, welcome to learning. I mean, that's what they say. That's why, what they say, for every hour in class, 3 hours outside of class, you're supposed to be working. Well, okay, well, how are you going to learn? That's how you learn. The learning is not done in class. It's a supplement to the learning. A supplement. Do you have a question? No, I didn't know if you were raising your hand. So here's a very useful theorem that's important to us. So A is congruent to B mod N if and only if. Now this is a very useful fact. So now the notation is going to go to what we wrote down earlier. If and only if the remainder when we divide A by N is equal to the remainder when we divide B by N. So, and this shouldn't surprise you. The only way, I mean, look at the example above. What's the remainder when I divide 17 by 5?
No, by 5.
Well, it'd be 2. What's the remainder when I divide 7 by 5? 2. So the only way they're congruent is if they have the same remainder when divided by n. So this is another, it's just, why is this useful? It might be useful. Look, when we state these theorems, we're giving you tools. We're giving you tools. When is it of use? I don't know. See, one of the issues here we have, and this is a part of the problem, and I was just saying this to another student this morning, is when you start getting into more advanced math classes, you have to get away from this, the math that you're used to, in which everything is, let's memorize a procedure, do it a bunch of times, learn a new one tomorrow. That's not really mathematics. That's like cookbook. That's procedures. That's not really math. And so what we want you to be able to do is we want you to be able to be a thinker, a problem solver, have a toolbox full of tools, and then learn when to apply them to answer more important questions, not just repeat the same algorithm 400 times and then do it a new algorithm tomorrow.
How do you like teach that to kids?
How do you teach what to kids? We're not teaching this to kids.
I'm not saying that. I'm saying literally the whole process.
I mean, kids actually would probably be better at this. They wouldn't, the notation would scare the hell out of them, but kids don't, not you particularly. One of the things I think we do when we're learning things that are new to us is we overcomplicate things. We try to make things more difficult than they are. Anytime, I keep saying this to you, if you want to understand modular arithmetic, just think about telling time, because that's how we tell time. What this allows us to do is this allows us to restrict the numbers we work with. We can take our number system and cut it down to any finite list that we want, and we can answer questions about it. So if you want to be mad at anybody for all this, actually the world is thankful, because modern internet and digital privacy doesn't exist without this. This is the fundamental stuff for how you can cash checks and bank online and order things on Amazon, and this is how it works. Well, it's not how all that works, but it's what keeps it secure. Oh, no, they don't, but there's someone programmed the computer so that when I order something from Amazon, I get billed properly, and then all the information is, the banking is done safely and securely. Google it. Google RSA encryption. Just type RSA encryption. You can learn why it matters. I don't think so. Don't they all do that now? I think, I'm not kidding, Jared. I think and maybe you're joking. It's hard to tell via text, but I'm pretty sure now Walmart and Kmart and all those places will get orders. They'll take your orders like a third party conduit, and then Amazon will ship it. All right, here's another important theorem. And by the way, don't forget there's context here. A and B can be any integers. N must be a positive integer. We said that from the beginning. Here's another theorem that I know that's what mathematics is. A is congruent to B mod N. And once again, this is if and only if A equals B plus Kn for some K.
Who do you think's gonna win the election?
Who do I think?
Not who you voted for, who do you think?
Oh, I don't know. I mean, it looks like Biden might win now. We'll see. We'll see. Yeah. Pennsylvania might have. I haven't checked. There's so much fighting. Like I said, it's ridiculous. One side thinks the other side's cheating, and the other people say they're cheating. It's just like, yeah, it's ridiculous. Yeah. And I think the interesting thing about the ballots is aren't all the ones that they're counting now, like in states like Michigan and Pennsylvania, I think those are the ones that were sent in weeks ago, I believe. I could be wrong.
They could be postmarked by yesterday.
Right, but I think most of them were sent in weeks ago. Like I know my parents sent theirs in like the very first day you could. But then the Democrats will say that the Republicans were trying to kill the postal service so that none of them got there. It's lots of excuses. Although it's like, I caution to mock anybody, but that's true, yeah. But I always find it funny, people like, they don't want to talk about, like, no one ever accepts blame. And I'm like, that's what kids do. Like, they like to blame each other. And I always find that funny. Like, I mean, maybe Biden does it too, but I haven't really noticed him do it because he hasn't been president for 4 years. But Trump, man, he loves to blame everybody else for everything. It's like, eventually it's just like, it's like the boy who cried wolf. Just shut the hell up already, dude. Yeah. But that's a good point. What's the old saying in sports, Jared? If you ain't cheating, you ain't trying, right? We could get into this topic stuff. I can laugh at the hypocrisies over and over again, but I don't want to do it. It's like the great line in the movie The Godfather, which probably none of you have seen, is when The Godfather. Have you ever seen it with like Al Pacino and that? Yeah, well, right. They're great movies. They really are, especially the first couple. But there's a great line when he's talking to the Senate. He's like, Senator, we're all part of the same hypocrisy. And that's really the truth. Everybody is a little creep.
I'm gonna make an offer.
You can't refuse. That's right.
And what he does, cut off them.
That's Scarface. Say hello to my little friend. You're over here.
No, it's no, it is Godfather first.
No, but he said, say hello to my little friend. Isn't that Scarface? That's Al Pacino in Scarface when he's like firing up. Scarface is great, but it's pretty much over. It ain't The Godfather. The Godfather's the best. All right. I did. I thought that was good.
What? Yeah.
You know a movie we just watched the other day? It was called, is it Outlaws? It was with like, who's the British actor? Tom. What is it? Huh? I thought you said something. I forget his name. But anyhow, it was about like bootleggers in like the early 1900s, like during Prohibition. It was really good. Yeah, he's in Peaky Blinders. What's his name? Tom something. I forget his name.
Tom Hunt. No.
Yeah, you got it. What is it? Tom. Someone Google that.
He's like, when a party comes in with the hell like this, you're gonna ask yourself, have I made a mistake?
Yeah. He's got the Peaky Blinders. You have to like watch it with subtitles because I can't understand what the hell they're saying.
You understand? I love
well, you might. You've got better language skills than me.
Wait, are you talking about the main guy?
Yeah, not the main guy in Peaky Blinders. He came in season C. Who?
No, Thomas Frank.
Tom. He came in the second season.
Tom Hunt. I love this.
Oh my God! You guys are the worst Googlers ever. Holy cow! Holy cow!
No, the main guy isn't like Tom Shelby anymore.
Tom Frank.
I'll figure this out. You guys are literally, honestly, you guys are literally the worst. I'll tell you what, you guys can't Google to save your life. There it is, Tom Hardy. Thank you. Very good, Tom Hardy.
Wait, put a picture up. Click on his name on there.
You know who he is. He's been in a ton of movies. There he is. He's a good-looking fella. Look at him, handsome fella.
He played that Jewish guy in the top. Like.
Yeah. I don't even know. No, I was thinking about the main guy.
Yeah, see, I know he didn't come into like the second season, but yeah, silly murder.
Fury, Legend, not Legend 2 Brothers.
I was just thinking of the character's name.
I didn't see. I never saw Venom. I don't watch. This, you guys are gonna get upset with me. I don't watch superhero movies. I am not watching.
I've got his video.
Yeah, that ain't happening on my watch. All right, we need to do. I don't know. I just don't like them. Why don't you like math?
I'm literally got a math teacher.
You just said you don't like math.
I said math's hard. I never said I didn't like math.
We've been watching one movie a week.
I watched Marvel in chronological order with quarantine. It was so good.
You guys are funny. All right, so Here's a cool fact that's very, very useful, and it's going to be another theorem. So you're going to get mad.
You mean this one?
Will Smith.
He doesn't age.
Now, he's a good-looking fella too. All right, here we go. So if I know it's a not, we're gonna have fun with these. So if A is congruent to B mod N, and if C is congruent, see what we're building is we're building a system of arithmetic so that we can solve problems. So think that this guy has sort of an analogy to solving equations. So if you have two congruences that are true, then there's this very nice and intuitive thing that happens that if you could sort of add them or move things around as you will. So these two properties are equivalent, or analogous, I should say. I shouldn't say they're equivalent, but these are analogous to what you sort of would have in when you were in algebra. If you have an equation, if two things are equal, and then you have two other things that are equal, you can move things from both sides of the equation. This is sort of analogous to that.
Before explaining this.
Is that from Peaky Blinders?
Yeah. Do you understand what he said?
No, probably not. No.
He said, when a pikey with a hair like this walks in, you gotta ask yourself, have I ever made a mistake?
Is that what he says? See, when I watched that show.
I don't know if you have a friend like this, he did, like kind of thing.
See,
You know the thing off the bar is called a smell. An Irish woman created it.
Really? There you go. So you learn something new every day. Who'd have thought they would learn about that?
There are Irish men, like Thomas Shelby, he is he's from Ireland. And he said, I prefer Irish whiskey over Scotch. And he just explained what I like.
It's very true. So, all right. So look, let me try to slow down for a second. So why do we care about these theorems? So there has to be a means to the end, right? What are we really interested in? And what we're interested in is we'd like to develop some sort of arithmetic so that we can solve problems. You know, you might not understand that now. You don't see the light at the end of the tunnel, but again, our job is to eventually, what we're doing is we're sort of developing tools for us to solve types of problems. Now, you don't really know what those problems are yet, but you're going to see soon enough. And it's going to be useful for us to talk about doing addition in modular arithmetic. So this is kind of where, before we leave, I want to hit this point because this is where the clock time, what I was trying to get you to understand when I said, what time is it going to be 2 hours from now, right? So here we go. This is going to be fun. Yeah, I know. So we can do what we call arithmetic modulo N. So here we go. So we define Z sub n to be this set, 0, 1, 2, all the way up to n minus 1. So for example, just to help you understand this, what is Z sub 2? Z sub 2 is 0, 1. What is Z sub 3? 0, 1, 2. All right. So what is, you could keep going for fun. Let's think about the clock. We could say Z sub 12, which is 0, 1, 2, all the way up to 11. Of course, we don't really think of it that way. We think of it as 1 through 12, but it's the same structure.
Is it important that you did n minus 1 and not n?
Yes, because I'm starting at 0. The idea is how many digits are in this set. There's n digits, right? So there's 2 digits in z sub 2. There's 3 digits in, and you might say, well, why do we have 0 instead? I mean, really, when you get down to it, the structure doesn't matter. I can write down A, B, C, D, E, F, G, and then you can create an arithmetic on it. But it's nice to keep it with our traditional numbers because that's familiar to us. So there's branches of math that take advantage of these structures. It's called, some people call it abstract algebra, other people call it modern algebra, where you study structures of sets and operations on them. It's pretty interesting stuff. Anyhow, so we can define addition on it. So what we do is we define addition. So for the time being, we're going to be very specific. We're going to put a plus sign with a subscript n. What is it going to mean? So if I say I want to add 2 numbers, A and B modulo n, that means this is equal to, you add the numbers and then you take the remainder mod n. And then similarly, we define multiplication. So that looks scary. So let's quickly, don't let this scare you. We're going to just do an example quickly. Well, eventually, when you get the hang of this, we'll stop putting these subscripts because context will tell us what we're doing. But let's just look at an example. What is 11 plus 2 mod, say, 12? Well, this would be 11 plus 2 mod 12, which was talking earlier. So this would be 13 mod 12. So what is the remainder when you take 12 and the 13? It's 1. No, I didn't say no, but I asked you to think. No, I asked you to think about it in terms of remainders. But maybe I asked it in a weird way and that confused you.
Probably.
Yeah. Does that make sense? What if we did the other one? What is 11 times 2 mod 12? Well, that would be 11 times 2. What is the remainder when we plug 12 in that? So that's 22 mod 12. So how many times does 12 go into 22? Goes in once with a remainder of 10. It's such an unfortunate thing that once you learn how to do it, it's so, yeah.
Why did we just 11 times 2 mod 10? We just multiply 11 to 2, then mod 12. Like we could do 11 mod 12 times 2 mod 12. Which would
Well, does that always work? How do we know that always works? I mean, you can't do mod 12 into 11. That doesn't make any sense.
Like it always works. Must always work.
Does it? I know what you're saying.
It's a bigger number. It must work.
So one of the things that this allows us to do is it allows us to just play with a set of numbers that we don't have to really worry about every number. We can say, okay, we're just going to look at structure instead of this endless list of, say, integers. So it's not going to be clear to you now why that matters and all that. But by the way, what's nice to note is this arithmetic is well defined. All the things that you're familiar with like addition and multiplication, like commutativity, associativity, inverses, distributing, all that holds. So anyhow, we'll let you think about that, and we'll talk more on Monday. All right, take care, everybody. Thank you very much. Got home. I don't know why. I guess I should have had my mask on. I feel bad. I didn't do that. I apologize. Stop.
Is homework time the last homework?
No, we're gonna have a couple more. You gotta have more.
Oh, speaking of that.